Hello everyone, myself is Dinesh and my roll number 536 and my topic is about explain spatial filtering. Spatial filtering. Filtering is a technique for modifying or enhancing an image. Filters are divided into two types, linear, also called convolution, and non-linear. A convolution is an algorithm that consists of recalculating the value of a pixel based on its own pixel value and the pixel values of its neighbors weighted by the coefficients of a convolution kernel. The sum of this calculation is divided by sum of the elements in the kernel to obtain a new pixel value. When to use? Spatial filters serve a variety of purposes such as detecting edges along a specific direction, countering patterns, reducing noise, and detail outlining or smoothing. Filters smooth, sharpen, transform, and remove noise from an image so that you can extract the information you need. Non-linear filters either extract the contours, edge detection, or remove the isolated pixels. Nonlinear vision has six different methods you can use for contour extraction: differentiation, gradient, pivot, Roberts, sigma, or Sobel. The canny edge detection filter is a specialized edge detection method that locates edges accurately, even under low signal to noise conditions in an image. To harmonize pixel values, choose between two filters, each of which uses a different method, that is nth order and low pass. These functions require that either a kernel size and order number or percentage is specified on input. Spatial filters alter pixel values with respect to variations in light intensity in their neighborhood. The neighborhood of a pixel is defined by the size of a matrix or mask centered on the pixel itself. These filters can be sensitive to the presence or absence of light intensity variations. Spatial filters fall into two categories. High pass filters. High pass filters emphasize significant variations of the light intensity usually found at boundary of objects. High pass frequency filters help isolate abruptly varying patterns that correspond to sharp edges, details, and noise. Low pass filters. And second one is low pass filter. Low pass filters attenuate variations of light intensity. Low pass frequency filters help emphasize gradually varying patterns such as objects and the background. They have tendency to smooth images by eliminating details and blurring edges. The following table describes the different types of spatial filters. Filter type filters linear, and in linear there are four types of filter types: linear high pass filter, and in linear high pass filter gradient filter and Laplacian filters are present, and in and second linear low pass filter there are two types of filters: smoothing and Gaussian filters, and in non-linear high pass filter there are five types of filters: gradient, Roberts, Sobel, Prewitt, differentiation, and sigma. Nonlinear low pass filter is having three types of filters: median, nth order, low pass. Linear filters. A linear filter replaces every pixel by a weighted sum of its neighbors. The matrix defining the neighborhood of the pixel also specifies the weight assigned to each neighbor. This matrix is called convolution kernel. If the filter kernel contains both negative and positive coefficients, the transfer function is equivalent to a weighted differentiation and produces a sharpening or high pass filter. Typical high pass filters include gradient and Laplacian filter. If all coefficients in the kernel are positive, the transfer function is equivalent to a weighted summation and produces a smoothing or low pass filter. Typical low pass filters include smoothing and Gaussian filter, gradient filter. A gradient filter highlights the variations of light intensity along a specific direction, which has the effect of outlining edges and revealing texture. For a given direction, you can design a gradient filter to highlight or darken the edges along that direction. The filter actually is sensitive to variations of intensity perpendicular to axis of symmetry of its kernel. A gradient convolution filter is a first order derivative. In this slide we can see that the first figure is the source image, and in second image a gradient filter extracts horizontal edges to produce the following image. And in third image, we can see that a gradient filter highlights diagonal edges. Laplacian filter. A Laplacian filter highlights the variation of the light intensity surrounding the pixel. The filter extracts the contour of objects and unoutlined details. Unlike the gradient filter, it is omnidirectional. The Laplacian convolution filter is a second order derivative. In this, and the first figure is the source image, and in second figure we can see that a Laplacian filter extracts contours, and third filter we can see that a Laplacian filter highlights contours. A Laplacian filter extracts the pixels where significant variations of light intensity are found. The presence of sharp edges, boundaries between objects, modification in texture of a background noise, or other effects can cause these variations. The transformed image contains white contours on a black background. Smoothing filter. A smoothing filter attenuates the variations of light intensity in the neighborhood of a pixel. It smooths the overall shape of objects, blurs edges, and removes details. A smoothing convolution filter is an averaging filter. In first figure we can say it is source image, and in second image it is smoothing filter. Second image we apply the smoothing filter. We can see that the blurriness is removed from the first image to produce the second image. Gaussian filter. A Gaussian filter attenuates the variations of light intensity in the neighborhood of a pixel. It smooths the overall shape of objects and attenuates details. It is similar to smoothing filter, but its blurring effect is more subdued. A Gaussian filter is an averaging filter. In this table, you can see that this is a kernel, and in second table it is 3 by 3 matrix, and in third table it is 5 by 5 matrix. Because all the coefficients in Gaussian kernel are positive, each pixel becomes a weighted average of its neighbors. The stronger the weight of neighboring pixel, the more influence it has on the new value of the central pixel. In second table and third table, the central pixel is highlighted, and its influence is more on the image. Unlike a smoothing kernel, the central coefficient of a Gaussian filter is greater than 1. Therefore, the original value of a pixel is multiplied by a weight greater than the weight of any of its neighbors. As a result, a greater central coefficient corresponds to a more subtle smoothing effect. A larger kernel size corresponds to a stronger smoothing effect. Nonlinear filters. A nonlinear filter replaces each pixel value with a nonlinear function of its surrounding pixels. Like the linear filters, the nonlinear filters operate on a neighborhood. Nonlinear Prewitt filter. The nonlinear Prewitt filter is a high-pass filter that extracts the outer contours of objects. It highlights significant variations of the light intensity along the vertical and horizontal axis. Nonlinear Sobel filter. The nonlinear Sobel filter is a high-pass filter that extracts the outer contours of objects. It highlights significant variations of the light intensity along the vertical and horizontal axis. As opposed to Prewitt filter, the Sobel filter assigns a higher weight to horizontal and vertical neighbors of the central pixel. In nonlinear pivot and nonlinear Sobel example, the this image is a source image, and in an under slide, the the second image under slide, the first image is we apply a nonlinear pivot filter, and in second image we have applied nonlinear Sobel filter. Both filters outline the contours of objects because of the different convolution kernels they combine. The nonlinear pivot has the tendency to outline curved contours, while the nonlinear Sobel extracts square contours. The difference is noticeable when observing the outlines of isolated pixels. Nonlinear gradient filter. The nonlinear gradient filter contours where an intensity variation occurs along the vertical axis. Roberts filter. The Roberts filter outlines the contours that highlight pixels where an intensity variation occurs along the diagonal axis. Differentiation filter. The differentiation filter produces continuous contours by highlighting each pixel where an intensity variation occurs between itself and its three upper left neighbors. Sigma filter. The sigma filter is a high pass filter. It outlines contours and details by setting pixels to mean value found in the neighborhood. If the derivation from this value is not significant, the example on the left shows an image before filtering. The example on the right shows the image after filtering. As you can see, the image on left shows before filtering, and the image on right shows image after filtering. Low pass filter. The low pass filter reduces details and blurs edges by setting pixels to the mean value found in the neighborhood. If the derivation from this value is large, the example on the left shows before filtering, the left and example on the right shows image after filtering. As we can see, the blurry edges are being performed. The filter has been performed. Median filter. The median filter is a low pass filter. It assigns to each pixel the median value of its neighborhood, effectively removing isolated pixels and reducing detail. However, the median filter does not blur the contour of objects. You can implement the median filter by performing an nth order filter and setting the order to f square minus 1 by 2 for a given filter size of f into f. Nonlinear filter. The nth order filter. Nth order filter is an extension of the median filter. It assigns to each pixel the nth value of its neighborhood when they are sorted in increasing order. The value n specifies the order of the filter, where you can use to moderate the effect of the filter on the overall light intensity of the image. A lower order corresponds a darker transformed image. A higher order corresponds to brighter transformed image. That's it. Thank you.